Excuse me. Welcome. All right, so this is part 4 of our game theory lecture, talking about dynamic games and subgame perfect Nash equilibria, which is just the version of Nash equilibrium that we can apply when thinking about games that have multiple stages and a dynamic element to them. So we've got a few setups here to go through. This is a game that I actually usually play in class with a couple of volunteers to demonstrate some of these ideas. But today we'll have to just pretend. So the idea here, right, is that we have two different players that take turns making a choice, whether to continue the game or end the game. And in each stage, right, if they end the game, then they get the higher payout, and some possible payout goes to the other player as well, with the exception of the very first stage, at which if player 1 chooses to end the game right away, they get $2 payout and nothing goes to player 2. Okay, so one quick side comment. I have inflated the payouts of the game a little bit more than when I play it in class, because I don't have $144 to potentially give away to students. Right, so the idea here is to figure out what we would expect rational players to do when they have this systematic game where, right, by passing the game on and letting it continue, they are increasing their potential payouts. Note that every time it becomes player 1's turn to choose again, they double the amount of money they would win. And same thing, every time it is player 2's turn to choose, they're doubling the amount of money that they would win. But in between each of those choices, their opponent also has an opportunity to call an end to the game. And so what would be the most rational way to think about strategy in this setting? What I will propose, and what is the underlying kind of thrust of subgame perfect Nash equilibrium, is that we want to use backwards induction. We want to think as far forward into the game as we can and see what would be the rational choice, and then move backwards from there to infer what the rational strategy is at every stage, right? And so that is where we get this term subgame perfect Nash equilibrium, because a subgame, the way that we're defining it, is from any point in a decision tree. This is also a decision tree over here, right? All of the remaining decisions from that point on, right? If we can cut to a single decision node, right? Each of these are decision nodes where a player makes a choice, takes an action, right? That's part of their strategy profile. So this is a subgame of the overall game here. And this is a smaller subgame of the overall game. And you could even think of sort of a redundant subgame being the entire game that we have here. So subgame perfect Nash equilibrium is to take it down to the smallest subgames and then move backwards from there. So we'd start right here, right, with the very last decision there. That is the smallest subgame of this overall game, and see what the Nash equilibrium concept would be for that game, right? So we're down to just player 1's choice right here. And what are they doing? They are effectively just choosing between 64 or 48, right? So what we know is that player one should choose to end the game right here, right? And get the 64 as their payoff. So that is the Nash equilibrium outcome for the smallest subgame. And now we go up to the next level of subgame, right? And taking as given what will happen in that last subgame based on the dominant strategy that we have identified, right? So now when we look at player two's choice, it's really just a logic game of saying, all right, player two knows what's going to happen in the next stage of the game, right? That if player one is rational, they will choose to end the game and gain the highest payout for themselves. And so player two knows that they can never get to that $48 payout, right? Or excuse me, the $96 payout. That they have 48 today, or they can continue the game and they'll only end up with 32. So player two wants that and will end the game in this second smallest subgame, right? Well, if that's the case, then coming back to the next smallest subgame, right, where player one is choosing at this decision node here, and player one knows that if they don't end the game, it will end with player two ending it in the next stage. So if they're at this decision node, then player one will want to take the $32 payout, right? Meaning that the game would end there. Which means we'd never get to this one down here, but that's fine. Now going back to the next smallest game, again, right? Player two knows that they're choosing between 24 or 16 in the next round, and so player two ends the game then. And player one would choose to end the game here. And therefore player two would choose to end the game here, and therefore player one would choose to end the game here, and therefore player two would choose to end the game here, and therefore player one would choose to end the game, and player two would choose to end the game in their very first turn and just take their $3 payout, which means that the rational choice for player one is to start the game by saying, I'll just take the $2 and end it here, right? Now, this may make you curious about how rational either the game is, the conditions that the game are imposing, or how much our ideas of rational choice really apply to individuals, because I'm sure you would presume that if I did play this in class, right, I could afford to pay out on that one, but my problem would come in that that when we run the game in an actual simulation in class, the game doesn't end immediately like we predict here, right? So there is somewhat of a disconnect, right, between rational choice and rational choice in theory and rational choice in application, because essentially because we understand that the people that we interact with don't always behave perfectly rationally, right? So if my expectation is that there is a chance that player two will keep playing the game because they're interested in trying to get to these higher payouts, and even if that chance isn't one, then that's going to change. Then I'm comparing, all right, I've got $2 now, I can double that by taking the chance that player two will also be looking forward and hoping to increase their payout. So there is a sort of, with small amounts at stake, right, a willingness to take on risk that kind of breaks away a little bit from the assumptions that we're making here about these strict pure strategies that the players should be taking. But the principle still applies, right? So effectively, we're saying that we can't predict players' exact strategies at times because they're willing to make somewhat of a trade-off, gambling the small amounts at the beginning in order to get to the higher dollar values out here. But the principle is still going to apply. We're never going to get down to here, right? Because we all know exactly what's going to happen in this very last decision here, the smallest subgame. Player one is going to take that, as long as we don't allow some sort of arbitrage where player one colludes with player two to divvy up this total payout in a different way, right? Which, to be clear, that sort of collusion is breaking the conditions of the game, right? The payoffs are no longer what we've laid them out to be if the players are able to collude with one another in a way that is enforceable among them. Right, so subgame perfect Nash equilibrium, right, is take each of the individual subgames and have a Nash equilibrium in each of those and use them with backwards induction to infer what happens in each of the previous stages of the game. So that is going to generally be how we approach sequential games and think about rational expectation of what should happen in a sequential game. And let's take that now to a static game like we started with, and then compare what happens as we transition from static to sequential. So first, let's think about Starbucks and Dunkin' setting their prices as high, medium, or low, and their profits here. So as in the previous part of the lecture, right, my recommendation is always going to be to look for best responses. So let's start with Dunkin's best response to Starbucks choosing a high price. Dunkin' can earn 1, 2, or 3. That's their best response is a low price if Starbucks chooses high. And if Starbucks chooses medium, Dunkin's best response is they can earn 3, 4, or 5. So 5 is Dunkin's best response there. And if Starbucks chooses a low price, then Dunkin' can earn 5, 6, or 5. So there's their best response there. Now switch it around. Suppose that Dunkin' chooses a high price. Then Starbucks is choosing between these first payoffs, and 3 is the best that they can do. If Dunkin' chooses a medium price, then Starbucks is choosing between 3, 4, or 5. I have already identified a Nash equilibrium here because both players are playing a best response. However, it is possible to have a second Nash equilibrium if one of these were also a best response for Starbucks. But when we look at Starbucks' best response when Dunkin' chooses low, Starbucks is choosing between 5, 6, and 7. So that's their best response there. Right? Note that Starbucks' best response is always low, right? They're 3, 5, or 7, and that is always better than what they would have earned if they were to choose medium or a high price. What that means is if I had started by looking for Starbucks' best responses, then really I could have identified the unique Nash equilibrium by just looking for Dunkin's best response to that one strategy for Starbucks. That's like Starbucks is never going to choose a different strategy, right? So the with Starbucks' dominant strategy here, we have a Nash equilibrium with a low price for Starbucks and a medium price for Dunkin'. Now, change this game to, rather than Starbucks and Dunkin' choosing simultaneously, Starbucks chooses their price first, and then Dunkin' reacts knowing what Starbucks' price is. So our Nash equilibrium concept here is going to be look at each of the sub-games, right? And decide what the optimal strategy is, or the best response / dominant strategy in just that individual sub-game, right? And then move backwards to the higher level sub-games and see what what the optimal strategy is there, given the responses that we predicted in the smaller games. All right, so at each of these individual decision nodes, we have Dunkin'. What I've done here, sorry, is broken this up into what is a decision tree, right? So Starbucks is moving first, and they can choose high, medium, or low for their price. And then we have 3 different decision nodes for Dunkin', right? One where what Dunkin's choice would be, given that it knows Starbucks has chosen high. Another one here, Dunkin's choice, given that it knows that Starbucks has chosen medium. And another one over here, it's Dunkin's choice, given they know that Starbucks has chosen low price. All right, so I look here. The structure of these payouts, this is just all of these payoffs transferred down into this format, right, is Starbucks up top, because they're the player that moves first, and then Dunkin' below. So Dunkin' is choosing between $1, $2, or $3 in payoff. This is the one that they like. Therefore, Dunkin' will choose low in that subgame, right? And over here, Dunkin' can choose between 3, 4, and 5. Again, they like low. So Dunkin' will choose low. And over here, Dunkin' is choosing between 5, 6, and 5. They like the 6, so they will choose medium. All right, so we're just taking each sub-game separately. We have an individual decision by one player, right? And seeing what their choice would be. And now, given those choices, I go back to Starbucks and see what their optimal choice is. Note that one would think that Dunkin' moving second, they get to wait and react to Starbucks' optimal choice. But and so that seems like it gives the advantage to Dunkin', right? But really, if we can predict how others will react to our choices, the advantage goes back to the first mover. It becomes a first mover advantage, right? Because Starbucks knows exactly how Dunkin' should react in each of these cases, because it knows, the assumption here is that it knows what these payoffs are for Dunkin'. So as long as Starbucks has a clear idea of what each of these payoffs are, then they look at this situation and they say, I can choose high, and I know that this is the payoff that I'll get if I choose high. And I know that this is the outcome if I choose medium, and I know that this is the outcome if I choose a low price, right? And this is where the kind of interesting part is, right? That means that Starbucks is choosing between 5, 6, and 5, and it's that 6 that they want, right? And so Starbucks chooses the medium price here, Dunkin' chooses a low price, and we get this outcome over here that was not feasible in the simultaneous game, right? Because Starbucks had this strictly dominant strategy. Starbucks would still prefer to choose a low price and get the 7 here, but they can't, right? They can choose a low price, but they know that they don't control Dunkin's choice, and so Dunkin will choose a medium price if so, and Starbucks will only get 5. But Starbucks is still able to improve its lot relative to the simultaneous game where they both make choices without any knowledge of the other. Starbucks is the one that is able to improve its outcome by choosing medium, knowing that because Starbucks is already committed to their strategy, Dunkin' will respond by choosing a low price and giving Starbucks the higher payoff in the outcome of the game. Right, so again, different application here, same idea. We're going to find a sub-game perfect Nash equilibrium, which is this outcome here, Starbucks choosing a medium price, Dunkin' choosing a low price, by taking each of the smallest little branches of the game and figuring out what the outcome of that portion of the game would be, and then using those to infer backwards what the optimal strategy is in the earlier stages of the game. Same thing we did here, just a different application. I should comment, I'm not picking necessarily the most interesting examples here. Your book has some pretty good ones. I think question 2.11 from at the end of chapter 13 in particular is a fun one about market entry and why a firm might actually pay for, or not pay for, but encourage regulation on themselves, even though it's costly to them, because it is less costly than having a market entrant. And so if that regulation would deter new market entrants, then it could be a profit maximizing outcome of that strategic game for the firm. Okay, I'm not going to erase that. So last example to cover here, right, is we're looking at Baxter and CDOG choosing whether or not to have advertising. If both firms choose not to advertise, then they both earn 40. If given that CDOG is not advertising, though, Baxter can choose to advertise and increase their profits to 50 at a significant loss for CDOG. CDOG can do the same, so it's another symmetric game. And if they both end up advertising, then their profits are half of what they would be otherwise. Note, right? Quick look at this as a static game. CDOG chooses no advertising. Baxter's best response is to advertise. CDOG chooses to advertise. Baxter's best response is to advertise. Same thing for CDOG, right? We have dominant strategy, Nash equilibrium, with both firms advertising. Now the question is, what happens if this game, right? So in this static one-time game, right? There is no way for the firms to get here because there's no way to win, right? They could agree that we're not going to advertise, but it's a one-off game. So after agreeing that we're not going to advertise, if you're running CDOG and I'm running Baxter, there's no reason why I wouldn't then say, well, actually, I'm going to, now that I'm actually making all my payments and decisions for the firm, I am going to advertise because that just increases my profits, right? There's no reason why these firms should trust each other. Excuse me. However, if this is a repeated interaction, then maybe there is, right? In a one-off thing, then I would deviate and choose the 50 because that's more profit for me. But if I know that in the following period, then we have this exact same interaction. So suppose these are monthly profits of 40,000 or 50,000 or 20,000, right? I know that next month we have the same sort of interaction, and if we agree not to advertise, I gain 10,000 this month by defecting on our agreement, right? But what I know is that if I do that, then next month you're definitely going to advertise as well, and I earn 20,000. Note that already in just that 1 month, in just those 2 months, my total profits will be 70,000, because the first month I defect from our agreement and I earn 50,000, and then the next month I've broken our agreement, and so we both advertise and I gain 20,000, right? So my total profits are 70,000, which is less than 2 months of cooperating with you and sticking with no advertising and earning 40,000 each month. So it is easily enforced if I know that that I have future periods in which we are going to continue having this exact same interaction. And that sort of collaboration could go on infinitely, right? We might think that Baxter and CDOG could happily go ahead and have this sort of non-competitive arrangement with one another to maximize their own profits. Except that if there is an end to the period in which they're interacting with one another, then this repeated static game no longer has the same threat, the same equilibrium where we continue to collaborate with one another, because defecting will lead to less profits in just 2 periods. All right, consider that that this is Baxter and CDOG. Those are monthly profits, but what they know is that there is a new brewery coming to town, massive operation that's being installed, and that's going to break up this whole happy collaborative, no advertising arrangement, because that brewery is going to come in very competitive and spending on advertising, and so we're both going to have to start advertising. Well, if I know that I have that there are 12 months of this repeated interaction remaining, then subgame perfect Nash equilibrium, right? The strategy is effectively the same as this. And the problem with trying to sustain it is I know that in the 12th month, in the last month, that we've been collaborating every month, but in that very last month, then there is no longer any future periods where you might punish me by us both advertising for all of the future periods and reducing our profits. So in that very last month, it is rational for me to defect on our agreement and earn the extra $10,000 in profits, right? Which means not only is it rational for CDOG to in that last month also defect, but CDOG knows that I'm going to cheat on them in the 12th month, and so in the 11th month they might say, well, I know you're going to cheat on me next month, so I'm going to cheat in November and try and capture that extra $10,000, because I know we're both going to be earning only $20,000 in December. Well, I understand the rational decision making of the owner at CDOG as well, and so in October I may say, well, it is only rational for CDOG to expect that we won't be cooperating in December and therefore defect in November. So I'm going to preempt them by defecting in October, and so on and so forth, back to the beginning, right? So the logical conclusion that I'm not going to prove here, though we could set up payoffs for various different examples of this, is that collaboration in a repeated game is unsustainable if there are a known and finite number of periods. To the game. Where by collaboration, I mean working together to achieve an outcome that is socially preferable, socially as in for all of the players involved, to an outcome that is a Nash equilibrium, right? If we're talking about an outcome that's a Nash equilibrium to begin with in a single stage of the game, then that's perfectly sustainable because it's a Nash equilibrium, right? But if we're trying to imagine some sort of subgame perfect Nash equilibrium that is achieving an outcome that is not a Nash equilibrium in a single subgame, then that is not going to be sustainable if there are a finite number of periods or stages to the game, and that number is known to the players. Because then the rational thing to do is to think about the last stage of the game, and if our non-Nash equilibrium is not an equal, if our desired outcome is not an equilibrium in that last stage of the game, right, then the whole thing starts to collapse backwards. Now, if it is not known, if there's some uncertainty here, then we could start thinking about probabilities and expected payoffs, and in a more complex sort of optimization problem, we could show that it might be possible to sustain an outcome that is not a Nash equilibrium of the single stage game. But this is the general result, right? Which is going to relate to firms trying to collaborate in markets to keep output down in order to keep prices high, as would a monopolist, because that is how they would maximize overall profits, but there's always an incentive to marginally produce more when you have multiple firms competing one against one another, which is what we'll see next week when we work with duopoly and the Cournot model and the Stackelberg model. All right. That is all for dynamic games. We will have one more short section where I'll talk about games with the players having continuous strategies.